Okay, welcome to the CERIAS Security Seminar at Purdue University. It is my great pleasure to introduce today Sheila Becker. Sheila is visiting Purdue from Luxembourg, so if you want to hear a lot about Luxembourg, you can ask her afterwards. And she is here today to tell us about how to secure application-level topology estimation networks and how to defend against a particular type of attack that has a very catchy name. It's called the frog boiling attack. So, Sheila.
Thanks for the introduction and welcome to my presentation. So we will take a look on the frog boiling attack today. So the frog boiling is an anecdote which describes a frog being boiled alive. This comes from the 19th century, where scientists have run several experiments, and they concluded that if you put a frog into a boiling pot of water, he will jump out immediately. But if you put him into cold water and you heat the water gradually, he will remain in the water and will be cooked. However, biologists say that this is not true. I don't know, I've never tried it. But this is often used as a metaphor in order to state that people are not always aware of gradual changes. And so this metaphor is also used in network security, where we can have an attacker who takes little steps in order to intrude into the system and not being detected. So, for instance, in intrusion detection systems, where the system monitors the system, where the intrusion detection monitors the system, and it will learn the behavior of the user as normal behavior, and it will relearn this behavior over time, and every time there is a deviation from that behavior, there will be an alarm raised. Now, an attacker can abuse this relearning process by introducing some small malicious changes into the normal behavior, and so that over time the bad behavior is considered as good behavior. Now, the goal of this work is to detect those attacks. Therefore, we use supervised classification techniques, and we do this for topology estimation networks, especially virtual coordinate systems. And to do so, we have to define an appropriate feature set. Furthermore, we also consider a more realistic attack strategies, where we define an attack sequences based on Markov model. So the outline of this talk looks like follows. I will first introduce you to the virtual coordinate systems and the attacks in those systems. Then I will give you an explanation over the more realistic attack strategies we consider in this work. I will show you the machine learning techniques we make use of, and I will define our feature set. And finally, we will take a look into the experimental results. So virtual coordinate systems have been proposed in order to correctly predict latencies between nodes in order to optimize performance, for instance, of peer-to-peer applications. In this work, we focus on Vivaldi, the algorithm which was proposed by Frank Dabeck. And here, the nodes of the real system are mapped into a virtual system, and nodes get syntactic coordinates. So node A gets coordinate XA, node B gets coordinate XB. So in this system, we consider that the nodes are connected by a spring, which is analogous to physical mass spring system. And so the length of the spring represents the estimated round-trip time between two nodes, which also means that the distance between the two coordinates is the estimated round-trip time. So, however, if the real measured round-trip time is different from the estimated round-trip time, then we have a tension on the spring, which therefore a node needs to update their coordinate. So if a spring is compressed, which means that the actual round-trip time is larger than the estimated round-trip time, then the nodes have to update their coordinates in order to be pushed apart. If the spring is extended, this means that the actual round-trip time is less than the estimated round-trip time, then the nodes are pulled together. To give you an idea about the update process, so let's assume we have node A and node B with the coordinates given here. So XA is 2 and 8, and XB is 5 and 9. So A sends a message to B, B replies to that message by sending its coordinates to the node A. Node A receives the coordinates, but also in the meantime the round trip time, the actual round trip time between the two nodes. So using the coordinates it has, it will calculate the estimated round trip time between the nodes and compares it to the actual round trip time. So they both differ, and the node A tries to approach the actual round trip time by updating its coordinates to get to a new coordinate -1 and 7. The main service goals of virtual coordinate systems is to have an accuracy and stability in the network. So accuracy describes the system of being able to accurately estimate the coordinates, and stability is the capability of the coordinates to converge. So we have, and attackers can influence this by the accuracy and stability by interfering with the latency estimations between the nodes. So here we have 3 attacks. So we have the inflation attack, where the malicious node reports large coordinates, and therefore the benign node will be pulled away from its correct position. The deflation attack, there the malicious node reports very low coordinates, and the benign node will be unable to move around in order to find its correct position. So those 2 attacks interfere with the accuracy of the system. The oscillation attack interferes with accuracy as well as with stability, as it reports randomly chosen round trip times. And here we can see an example of an oscillation attack. So we have in figure A, we can see that we have different group of nodes in the system. And in figure B, we have Vivaldi after the oscillation attack, and we can see that we can't really differentiate between the different groups. So this means that the oscillation attack leads to a chaos in the system. So there are already some defense mechanisms existing there. So we have, for instance, the outlier detection, where we have a spatial outlier detection, where a node has to be consistent in the updates it reports with what his neighbors reports, and this is based on a spatial threshold. The temporal outlier detection, there a node has to be consistent in what he reported in the past, so with his history, and this is based on a temporal outlier detection, and we have a combination of them too, so which are based on the spatial as well as on the temporal threshold. However, these defense mechanisms are shown to be vulnerable to those attacks. So we have the frog boiling attack, where an attacker performs an inflation attack, but in very slow steps, so that it will remain undetected as it remains under the threshold. The network partition is another kind of frog boiling attack, where a group of malicious nodes perform a frog boiling attack on different groups of nodes, and so the network will be partitioned. So we will consider more realistic attack strategies. Now usually the attackers are considered in the network to perform from the beginning till the end always the same attack, so that each attacker performs the same attack. And so we consider that first of all we have a random attack, where the attackers independently choose which attack to perform. And we have a new way to build attack sequences by using a Markov model, where we have different time intervals with different attacks. In this case, all the attackers perform at that spatial time interval the same attack. And here the recognition pattern becomes more difficult to detect. So the sequence attack is based on that Markov chain. This includes all the different attacks we know. So we have the inflation, deflation, oscillation, and we have the new advanced attacks of frog boiling and network partition. But we also have a state of no attack, in which the attacker will perform no attack. So this chain is a single communicating class, which means that every state is switchable by every state, and there are no restrictions on how often one state can be visited. The only requirements we made with this chain is that we started always in the no attack state in the beginning. So we have leveraged 20 different sequence scenarios for using this chain. However, we will not take a look at them all. We just focus on the most relevant ones. And we can group them in 3 different groups based on the amount of the non-attacking intervals. We choose to group them by this interval because as it has a great importance for the detection mechanism we use in this work. So we have sequences A and B, which have a non-attacking interval around 5%, a low amount of non-attacking intervals. Then sequences C and D have a medium amount of non-attacking intervals, around 25% of the whole intervals. And sequences A and F, E and F have a non-attacking intervals of 50%. So we use machine learning, but what is machine learning? So machine learning is a huge field, and it can be stated as a robot who has to learn to keep its balance. So if a robot will fall to the left side, he has 2 choices. Either he puts weight on the left side or on the right side. So if he puts the weight on the left side, he will fall to the left side. So the next time he will fall, he knows he has to put weight on the right side. But the next time he might fall on the right side. So if he tries the same, he will fall to the right side. And then he knows, okay, if I fall to the left side, I have to put weight on the right side. If I fall to the right side, I have to put weight on the left side. But machine learning can also be considered as programming computers to optimize performance using example data or past experiences. For instance, if we have an attack and we can define the characteristics of that attack, and we can see later on the same characteristics of a data again, then we can conclude that it's an attack. So, as I already said, machine learning is a huge field, and we cannot focus on this today on everything, but we just focus on the part which is important for us. So I grouped it into 2 different categories, the supervised machine learning and unsupervised machine learning. The difference between them is that in the supervised machine learning we have training data that from which the algorithm can learn how the data looks like and to which class it belongs. So we have a supervisor which can label the data. It either is an attack or not an attack. So we have the input as well as the output. And the algorithm will learn how to map the input to the output. So the algorithm will be able to define how to map the characteristics to be either an attack or not an attack. In the unsupervised machine learning, we don't have a supervisor, so nobody who can label the data. So we just have the input. And usually in this type of machine learning, algorithms choose the similarities between the different data points. So which method should we use? Well, we are running simulations and we are integrating the attacks. So we know how the system works, we know how the data looks like, and so we can define how it looks like, or what data is an attack and what data is not an attack. So we go for supervised machine learning. And so we only want to differentiate between 2 classes, so if known attack or not or attack, so we use classification. And also in classification we have many different choices. So in this work we compare decision trees to support vector machines. Decision trees is just the creation of rules where the observations made on the input data is reflected. And in here we compare 2 different decision trees. So we have the classification and regression tree and the C4.5. The difference between those 2 algorithms is the way how they compute the rules. And the support vector machines, there we map the input space into another dimensional space using kernel functions. And this is used in order to render the data linear separable. So here we can see an example of both. So we have the decision tree. So if we have the variable a and it's less than 0.5, then we will branch to node C. And if value C is bigger than 0.7, then we know we have an attack. In support vector machines, we can see in the above figure the input space, and we can see that it's hard to define. If you would have the colors, it's hard to define which data is in which class. So we try to have a function in order to put it into another dimensional space, which is called a kernel function. And in the figure beneath, we can see that we have separated the different data points by just drawing a hyperplane. The challenge in this work is how to define the correct feature set in order to detect the frog boiling attack, but also to be able to detect all the other attacks. So we have two examples of the same data points, the same input data. So in figure A, we have a deflation attack, and we can see that we can easily separate the different data points. So we can separate the non-attacking points versus the attacking points by just drawing a line. However, for the same input space, it is not feasible for the inflation attack. Here, it is not possible to draw just a line and to separate them. So this means that the feature set has to be well chosen in order to reflect all the properties of the different attacks. So first, on what will we base the feature set? So somehow the attacks all have an impact on the performance on the system. So we want to reflect that in the feature set, and therefore we use the local error. The local error represents the relation between the estimated round-trip time and the actual round-trip time. So okay, but how will we now, from this feature, going to detect the frog boiling attack? So well, we know the frog boiling attack goes into different time steps. So we have somehow to establish a temporal correlation between the data sets. That's why we use delta 1, where we have the local error at time t minus local error time at t minus 1. So those two features are shown in the figures below, where we can see that we have a change in the different time intervals. But even if we have a change there, if we would just take a look at one single point, we are not able to define if it's an attack or not, because we don't have the global picture, we just have that knowledge of that point. So we run several experiments in order to find how far we have to go in the past to detect the frog boiling attack. And we have seen that, or we have found that we need a 4-lag correlation. So we need to go back 4 steps in the time in order to be able to detect the frog boiling and also the other attacks. So that's why we use, as in figures C, D, and E, we use delta 2, delta 3, and delta 4 as the feature set. However, we realize that this is not totally enough. We also need to capture the discretized form of the second order derivative. Therefore, we have delta 1 at time t minus delta 1 at time t minus 1. Also, we want to get insights at the inflection points of that second order derivative. That's why we use absolute value of that. Now coming to our experimental results. So we used for the experimental setup the standard setup for Vivaldi, where we have a reference set of 64 peer nodes. And we use the peer-to-peer simulator in order to do our simulations using the King dataset, where we have a pairwise round-trip time of 1,740 nodes. And this represents larger scale peer-to-peer systems. But we also wanted to have a real results, real experimental setup. So we used the Internet Planet Lab testbed, and we ran experiments with 500 nodes. We have done evaluation in 2 setups. So we have the global setup and the local setup. The global setup is just where we compute one feature set for all the nodes. So we have we calculate the median local error considering all the nodes in the system. For the local setup, we focus on single nodes, so we don't compute the median local error, but just we take the local error in order to compute our feature set. So here we can see some properties for the classification. what is important is that we use the tenfold cross-validation. This means that we use the data set as training set as well as test set. So the training set is used to learn, so the algorithm can learn from it, and the test set, the decision tree or the function is just tested and to see how well it performs. Tenfold means that our data set is divided in 10 different slices. So we take 9 slices for the training purpose and 1 slice for the testing purpose. For this, we used Vika, an open source machine learning software. And we can see here different properties for the decision trees we used, which are the default ones. So they performed well. We didn't change anything on that. For the support vector machines, we used the library libsvm. We have checked and elaborated different kernel functions as well as parameters, but they didn't give us an improvement on the results, so we stick to the default one. So now let's take a look on the Planet Lab, the global setup, results for the inflation, deflation, and oscillation attack. So we run experiments for 10% malicious attackers, malicious users, 20% and 30%. So in those columns, we see the results for the decision trees. And we can see that globally, we have high true positive rates and low false positive rates. However, for the support vector machines, we have high false positive rates. So 20% of false positive rate is really high. Imagine 5 of every benign update is considered as being malicious. So here we can see the results for the advanced signal attacks, so the frog boiling, network partition, and the random attack. So again, we can see that the decision trees perform quite well. And we can see again that support vector machines have high false positive rates. Now for the sequence attacks, we can now see why it was important to classify the sequences into the groups of the amount of the non-attacking intervals, because we see that if we have a low amount of non-attacking intervals, we have huge false positive rates. And the more amount we have for the non-attacking intervals, the better the false positive rate gets. This is because the classifier not only needs data for the malicious updates in order to know how the malicious updates look like, but also for the normal updates. So, and 5% is just not enough. It cannot learn enough how the normal updates look like. Now the local setup. We have done the local setup in order to be able to compare it to the outlier detection. So in figure A, we have the true positive rate for the outlier detection. It is not surprising that the frog boiling attack performs least in all the than the other attacks, as outlier detection is known to be vulnerable to that attack. In figure B, we can see the classification results for the true positives, and we can see that all the classification results for all the attacks perform much better than the outlier detection, not only for frog boiling, but for all the attacks. So when we have, in figure C, we have the outlier detection and the false positive rates. So, and we can see that we have a huge amount of false positive rates, whereas we have much better results for the classification results. So, just to clarify, in these block box diagrams, the black line is the median of the false positives, and the high line is the maximum, and the lowest line is the minimum of the data. So here we take a look at the sequence results for the local setup. So again, we can see for the true positive rates, we can see that outlier detection does not perform well in comparison to the classification results. But if we take a look at the false positive rates, then we can see that, okay, the median value of the false positive rates is still better than in classification than the outlier detection, but we have a huge maximum. And this is because we take a look at the single nodes, so there is a huge variation in different results. So what we have done here is we have faced the frog boiling attack. We have done the detection by using classification, and we consider for this in the feature set the autocorrelation between the different data points. We have used different or another kind of attack, like the random attack and the sequence attack, which was based on our Markov chain. We used supervised classifiers, so we used the decision trees, CARD and C4.5, and the support vector machines. So we saw that the support vector machines do not perform very well in comparison to the decision tree. And in the beginning we thought, why is this? Because usually support vector machines perform much better than decision trees, and the reason is that the data is just not linear separable. So, and also if you compare it to the outlier detection, then our classification results perform much better, except for the sequence attacks where we have high variance in the false positive rates. So as future work, we want to integrate the decision tree in the system, but then we have to reduce the false positives, especially in order to face problems for the sequence attacks. And then if we have integrated the decision tree, how will we go to the next step and how will we mitigate the attack once detected? So we have somehow to get a more fine-grained classification in order to be able to define from where the malicious update comes from. And also another idea would be to use another kind of support vector machines, so the piecewise linear separable, and not only the simple support vector machines, as this would help to improve the results for the support vector machines. So thanks for the attention, and any questions?
With regard to your sequence attacks, have you tried to see if there is any kind of a distribution that the attacks follow? Because if you do happen to map it to a certain kind of a distribution, then you could, use it as some kind of a recognition as a pattern in which, the attacks might come up to.
So in general, the sequence attacks consider all the different attacks. So there's no one line. I mean, we could, of course, go into deep inspection and see if there's a relation between the different attacks. Because also if we take a look at the 50% non-attacking intervals, we have a difference. So this might, of the results, so this might lay in the attacks itself. Any other questions? Thank you.